Welcome back, everyone. This this session will be delivered by Dr. Uday Mandal sir, who is a senior scientist specializing in soil and water conservation engineering, Dehradun, with a PhD from IIT Kharagpur. He has over 11 years of expertise in soil erosion management, water conservation, and environmental stewardship. He has published numerous papers in various journals covering soil erosion management, water conservation, environmental stewardship, and water conservation techniques. Sorry, sir, we have lost the connection. सर डायरेक्ट टॉपिक क्लिक कर दीजिए. Now, I would like to brief the topic. Remote sensing and GIS are instrumental in groundwater potential zoning map. RS provides spatial data on landforms, vegetation, and drainage patterns, while GIS integrates this with slope, soil, and geological information. This helps identify recharge zones, assess groundwater availability, and support sustainable water resource management. Now, I would like to invite Dr. Uday Mandal sir to share his valuable insights with us. Sir, please.
Thank you very much for your nice introductory remarks. And am I audible? Am I audible?
Sir.
Am I
Yes.
audible?
Yes,
Please.
sir.
Yeah. So may I start with? Please, someone respond just for initially so that I
Yes,
can
sir.
start. Yeah. So just I would like to know the basically the trainee or that workshop is the student or some. If you just give one background little, just who are those?
Sir, most of the participants are students.
Okay, okay. Okay, fine, fine. So, I am just sharing my presentation.
Yes, sir.
Hello.
Yes,
Not yet visible, I hope.
It's not visible now. I think you have not shared your screen, or is there is any technical glitch? It seems it's still showing presenting. Oh, now it's fine. Huh?
But it is not in slideshow mode,
No.
na?
Yeah. No, it's fine.
PPT, because PPT is big size, that's why I was trying to avoid it. Okay, now it is visible,
Now
Yes,
it's fine. Huh?
but it is not in presentation mode. Hello?
Sir, please put the presentation mode first, then you select the window or the presentation window, and then you can continue the.
Oh, okay. Thank you. Just it is not coming presentation mode. Please guide further.
Sir, press F5.
F5 is not responding actually. I am doing that one.
Okay, sir, you can try sharing the entire screen.
Okay, entire screen.
Yes, sir.
Okay. ये तो
Okay, sir, now you can switch it to the presentation tab
F5.
and minimize it, sir. Just minimize the Chrome and open your presentation tab.
Okay.
Now it will work. Yes, sir.
It is working?
Yes, sir. And sir, you can hide that one.
Yes.
Yes. Okay, now.
Thank you.
Yes, sir. It's okay now.
So good afternoon, everyone. Myself Uday Mundal. Just I'm trying to convey some message that how we can utilize that remote sensing and GIS for the betterment of the groundwater potential aspect. So I will cover just introductory part like that, why it is so important and what is delineation, something kind that. Then what kind of literacy is available and how we can go further. Then objective and study area methodology, result discussion and summary and conclusion and acknowledgement. So just if we see in briefly in this figure that surface water initially India having that 14% irrigation due to in 1951 that by the groundwater, but if we see presently it is increasing actually just reversely. So surface water is coming down, utilization of the surface water. So it is now less than 30 and it is from 30 or onward it is going upward even 60. And this is report by agriculture statistics at a glance. So you can imagine that how much pressure actually we are actually giving on the groundwater resource, actually which is sometimes say replenishable. And and similarly, the India is also the largest groundwater user. That World Bank report says the total annual groundwater recharge is 437.60 billion cubic meter and extracted as the 239 approximately. That is also reported by the Ministry of Jal Shakti. in 2022. And 42% of the extracted groundwater are utilized in the agriculture only. So whatever we are extracting the groundwater, it is totally 42% is utilizing in the agriculture sector only. So India uses 25% of the all groundwater extracted globally. So globally, of total, India is using 25%. About 70% of the water supply in India and agriculture today is groundwater. So this, and at the same time we know that pumping here and there, we are just creating, we are digging the well, we are, because today's context we don't have the limitation of the economy. Simply we are digging and we are taking out without concerning anything that how much it is there, what source it is we are going, and when it will be fill up further. So we are bothering, we are not bothering at all, just randomly we are pumping out. So for that reason we can say sometimes coastal belt, the ground seawater intrusion is taking place in Punjab area, northern India, and some the Indo-Gangetic belt. So groundwater table in drastically it is going down. So at this moment how we can plan for better way, and where we can, from where we can explore the further groundwater resource available or not, and we can utilize this further. So satellite based remote sensing provide some kind of data which may be useful, and we will see over the time that how we can utilize this remote sensing and GIS to cope up the finding the potential of the groundwater. And this map actually showing that it is also a satellite product, and Rodin et al. Published in 2019 and published in Nature. So this map basically showing that percentage of groundwater withdrawal as a percentage of recharge. So whatever recharge is going on, and then how much we are taking out. So if you see the Punjab, Haryana, Rajasthan, we are taking out more. But the hydrology, but for that to manage that groundwater, we need the hydrological information, ground survey, or geological survey. So it is actually basically tough things, and it is a huge money involvement. So how we can make the GIS along with the MCDA multi-criteria decision making tool to delineate the groundwater potential zone, and with faster way and with economic way, and further we can explore the possible area. So before that going to the topic, actually just I want to highlight that what is delineation. Delineation is process of defining or marking the boundaries or features for a purpose, for the features of for a purpose of analysis, management and decision making. And then what is groundwater potential zone then? So we can define as the designated area that reflect the likelihood of finding groundwater in a particular region. And what is groundwater potential zone delineation? So it's basically systematic approach, and in which we can delineate the boundary where would be the highly potential zone, where moderate, low or very low. And that high, moderate, low, very low, then it is a subjective word, you can change also accordingly. But basically it's a delineation or demarcation of the different prospect status of the groundwater resource. Then map this area to provide a visual representation of the groundwater potential, provide a framework for groundwater management, planning and decision making. Then why groundwater potential zones delineation? Sustainable groundwater management, water supply planning, water quality protection, environmental conservation protection, effective land management, agriculture development, and protecting agriculture productivity also. And now, what are the method of the groundwater potential zone delineation? That is a conventional method, as I was trying to convey that it is a geological, geophysical investigation, drilling, or field survey. And other method in the right hand side, that is a modern technique or modern method we can say, that is a GIS and remote sensing application. So actual measurement is highly complex and time consuming and costly affair. But GIS and remote sensing can do with minimum time and minimum risk and minimum expenditure. And GIS and RS tool having the spatio-temporal presentation capacity. So we can visualize where actually the prospect are there, where is not there. So this is a One another good option that instead of point or instead of textual data, we can visualize in image form where actually the groundwater potential zone status, where we can do plan or exercise anything what we want. Now, what is remote sensing? It is I know that everyone know what is remote sensing. Just for your information, it's a collection of information without touching any object, for analyzing, for processing, and for visualization. And then what is geographic information system? Now, it is a powerful tool used for collecting, storing, analyzing, managing, and visualizing spatial and geographical data. So with the help of, so remote sensing alone we can't do anything unless until we don't have GIS platform. So GIS basically is a tool and remote sensing is a data or information. So I'm not going into the review literature part, but it is for as the student they are taking the part of this workshop, so they should understand that why actually it is required. This is actually basically says the past literature, past what people are did, what you can do, what you are going to do. So is there any novelty or not? So to understand that past experience, what many authors already conducted similar kind of studies and what they found, what methodology they have utilized. So based on that, actually you can plan your study for research or for exploration of any kind of, not only the groundwater potential zone exploration research, many direction you can find out it. So a spatial prediction of groundwater potential zone depends on various features like land use, land cover, geomorphology, hydrogeology, soil surface geology, recharge rate, drainage density, rainfall, slope, surface water body, lineament density, NDVI map, etc. Worldwide, many researchers was utilized different features as per the study convenient for the prediction of the groundwater potential zone map. So this table, very comprehensive presentation of the various researches globally, including India, what kind of parameter can be utilized for delineation of the groundwater potential zone. So in the top, you can see the in abbreviation form, the parameter name was written, and left hand side, and then under the reference column, you will find the reference of the literature available. This is only few, you can search so many literature available, and but this table will show you at a glance and which author utilize which kind of parameter and how they come into conclusion and what kind of accuracy they have received. So if you go through this literature individually, you will find so many things, but in this tabular form you will find at a glance different parameter and maximum kind of parameter. So this is maximum. Sometimes you will find that RC means runoff coefficient. It is though it is not directly part of the groundwater or runoff quantification, but sometimes people are using the runoff coefficient. So one author, that is Singh et al. 2018. So these are the maximum number of parameter people have used for delineation of the watershed. And now also they have used some, once you have so many parameter, there is a question how you will utilize that parameter, how you will give the weightage. So there are so many weightage are methodology are there. We will see the kind of methodology. So here initially I will discuss that ASP, or you can say multi-criteria decision making tool, which is sometimes we call analytical hierarchical process. It is developed by Satie et al. 1980, and I will explain how you give the weightage. So basically, ASP do the pairwise comparison. So for example, land use, soil, and we have seen so many parameter. So just I'm going back. So for example, you see the land use, land cover, soil, and so which one is more important? Say for land use and soil, and I will compare with these two. Then I will compare with the soil geomorphology, then land use with geomorphology, land use with geology, hydrogeology. So land use with drainage density, rainfall. So each and every, it's a combination. Suppose we have 10 parameters. So each and every parameter I have to compare pairwise, and I have to make a matrix to analyze to finally get the weightage value instead of simply normalized or arithmetic average. Suppose we have rank out it, and we have sum of the rank and individual rank divided by sum of the rank. That way we can get also, but it's a very simplified way. So here we are going to discuss the ASP, that analytical hierarchical process. And so these are actually people are used that, as I was telling, that GIS remote sensing. So all whatever literature I am mentioning here and the tabular form I have presented, so all are using GIS platform, and like ASP, like that frequency ratio method, like weight of evidence, like gray analytical hierarchical process. There are so many methods, so they are using it. Okay, and simply normalize weightage method. Okay, so based on the literature review and that previous information, so here where our objective I have defined based on the topic given to me, that to identify the groundwater potential zones and its validation. Am I audible? Please, it is going fine. Please respond, anyone.
Yes, sir.
So it's smoothly it's going. Okay,
Yes, sir.
thank you. So, for a study area, it's just kind of geographical location, it's a physical area. So that's why we need a area where we have applied this technology, and not only the apply. So after application, and we have to check that what I am going to predict or I am going to propose or prescribe something. Is it practically feasible, or it is useful, or it is not, or it is validated. So for that we need a physical area. So I have chosen my watershed is a Subarnarekha basin. Subarnarekha basin. Maybe it is you sitting on this river basin. I don't know exactly, but I hope that Rachi, Dhanbad, I think it is on the Subarnarekha basin itself. So this area actually 26,105 square kilometer area, and for conducting this specific research and groundwater potential zone delineation, I have chosen that three block of the Odisha district, that is Baleshwar and Baleshwar, Baliapal and Jaleshwar, three district uh, of the Odisha state, and which is the coastal, we can say coastal part of the Subarnarekha basin. And this topography, if we see that, and this study area is 823 square kilometer, and the land surface is basically mainly flatter, even though the slope variation, that the total elevation difference is 0 to 1172 meter, but this particular area, the 2 to 8% land slope is covering 80% area. And what is the methodology I have used in this study? If you see, this is conventional map, some, then SWOT model also, then remote sensing part. So it's a basically combination of remote sensing, and you can say some already existing conventional map with this the fusion of that all parameter, we are actually going to get that potential map. If you see carefully here, that conventional map, which kind of map we are using, that is a soil map, that surface geology, geomorphology and hydrogeology. These are the existing map. You will find that Geological Survey of India, then Soil Survey of India, or like then Survey of India, and soil map you will get from the National Bureau of Soil Survey and Land Use Planning, Nagpur. Then SWOT map. In SWOT model, we use that watershed delineation in through this SWOT map. Then using the DEM, using the land use, land cover, slope and weather parameter, we may able to get the recharge rate, and I will explain further in later. So then from the Google Earth engine, or Google Earth map, you will get the surface water body extraction. Each and it's like a like your pond level information we have extracted from the Google Earth image, and then using the dam we can make the slope map, then drainage density and lineament density. Then Landsat 7 that we can get that land use land cover map, and then normalized vegetation index, difference vegetation or NDVI. So using this map, we analyze, then we have make the layer that in ArcGIS tool, then preparation of thematic layer as I mentioned, then assign the weightage. That weightage will come from the analytical hierarchical process, then reclassify that GIS, and that weightage some of the thematic layer we have incorporated in the ArcGIS, that special analyst tool, that raster calculator, then generalization of the groundwater potential zone, then sensitivity analysis, and then validation of the map. So this is the whole method which is involved to estimate or to delineate the groundwater potential zone. Excuse me. So if you see the equation, so whatever I have mentioned, the layer I have used in this study, so this we can represent in this equation where this WK will be your the normalized weight of the ket feature, that is WK can be defined that GMK by GM, that F, and the geometric mean, then consistency ratio. And one important thing, and you see this is a this is just like denote the indicator function. What does it mean? So this equation actually representing, suppose in layer soil layer we have four classes. Say for example, in four class once, and we have the four weightage value. Okay, that is also coming using that ASP. And say for and now we have to multiply that actual weightage value of the soil. So we have initially 13 layer. So 13 layer having the weightage individual to based on the influence of the groundwater potential zone or prospect of the potential zone. So we have the that ASP, that weightage value. So and it will multiply with that individual features, sub features. So one features will multiply only, so one pixel basically ij, if you consider it's a pixel or features, so one features will multiply with that, the sub features will multiply. This is actually explanation and available in details if you're not getting in that Mondol et al. 2016 that published in Water Resource Management. So you will get in details. And next this, after that you have to go with the consistency ratio, then consistency index. So for consistency index or ratio should not be more than 10%. So once we will give the expertise weightage, or when we make the judgment matrix or pairwise comparison matrix, and after that if we have to check that my matrix or that weightage which I have given, it's the consistent. If the it is that CR ratio is more than 10, so we should not, that ASP telling that you should not go with that judgment matrix, so you have to revise it, then you will get the better result. And as I told you that sensitive analysis, so sensitive analysis is nothing but simply we can define it in absence of one parameter, how that outcome will change or how it will impact on the outcome. So it is and basically in this groundwater potential zone map, this is first time we have introduced this. Now you can see so many papers, but it is first time we have introduced in this publication that sensitivity analysis of individual parameter and define in this equation, where you can see that Si minus Ij is the jth type of groundwater potential zone area due to omission of I features. Okay, that's why it is indicating minus. And Sfj is the jth type of groundwater potential zone area using all features. and and I will also show you how we can find out the sensitivity of individual parameter, and also in tabular form I will show how it is actually impacting on the final groundwater potential zone prospect map. So here I have used this 13. I have that is land use, land cover, soil geomorphology, soil geology, surface geology, hydrogeology, recharge rate, drainage density, rainfall slope, surface water body, lineament density, normalized difference vegetation index, and few are that just drainage density. Maybe you are aware because it's very simple. There is a length of stream per unit area. You can define it's a kilometer per square kilometer, or mile per square mile, or meter per square meter. So lineament density, it's a length of the lineament line features of particular and then area. So in ArcGIS tool there is a line density tool is there, we have utilized that. Then NDY calculation, it's a direct we can calculate from the Landsat 7, 8, even that LIS 4, or any Iconos, QuickBird, whatever the satellite imagery is available, we can utilize that, and from that satellite imagery we can calculate the NDVI. So as I told you that recharge rate we have calculated in the SWOT, and then we have put into this, and we have make actually layer and then utilize in groundwater potential zone. So for that purpose actually we have used SWOT model. We have calibrated, validated of the SWOT model with the high efficiency, and then using this equation that we have calculated the everyday recharge rate based on the soil, based on the weather parameter, based on the uh, topography, and as I mentioned, the climatic, all climatic parameter. So daily and then monthly, we have summarized it, and this actually from SWOT model we can get it from the HRU level. Just HRU, I hope you all are know that is hydrological response unit. So it is a basically smallest unit uh, in which that SWOT can estimate each and individual parameter as well as output, and it can produce output. So from that HRU, that so basically SWOT does that is a basin, then sub-basin, then HRU. So or watershed, sub-watershed, or HRU. So these three layer SWOT basically delineate the demarcate the watershed, sub-watershed, or HRU boundary, and we will get in SWOT model that HRU level what is the groundwater recharge each and individual HRU. So then from the HRU, this equation is shows how we can convert that HRU recharge rate to sub-watershed or sub-basin recharge rate. So using this equation, and you see this is the sub-watershed we have delineated the total in this particular area, and we have the each and individual sub-watershed recharge rate, and this is a just pictorial representation how we can make it. So if you see, for example, that this is actually SWOT boundary sub-watershed, that is HRU1, area 2, and Richard R2. If you define this, so HRU2, area 2, A2, and R2, it's a different Richard. So how we can get this? So we have here, for example, 5 HRU. So so how will this is sub-watershed boundary or sub-basin boundary? So using this equation, that area weighted erosion equation, we can calculate able to calculate the basin wise or sub-basin wise the research rate, and this is actually not used directly here, just for showing to you. And that same data we can utilize in the groundwater modeling like GMS mode flow or visual mode flow. So in GMS and visual mode flow, normally people use the grid, and we can place our data in the grid format also. So this is basically the same recharge rate we can utilize for the groundwater potential zone map, and we can utilize this map as input to the another that modeling like groundwater modeling or subsurface water modeling using GMS or visual mode flow. So as I was mentioning that it is a ASP that is basically developed by the the SETI 1980. Uh, so how they have actually given the scale. So these are the scale basically when we will compare the pairwise matrix or among the two parameters, then what does it mean? One means that equal importance. Suppose land use and soil, there is no any difference, and we are thinking that these two parameters equally importance for groundwater prospect delineation, then you can put is a 1. Otherwise you can put some fractional value, or you can put 1 by 5 and say, and now 2 is equal to moderate importance, then 3, like that. So if you go with the details, you will find that, meaning if I am giving, say for example, land use land cover, and I am putting here that soil is more important than land use, and if I put here 9, that means uh, I am meaning it that soil is 9 times more important than the land use, while I will estimate the groundwater potential zone, or while I am going to delineate the groundwater potential zone. Say for example, soil, if you see here, 6 by 3, 6 by 3 basically it's a 2 actually. So soil is double important with the lineament density. And reversely, so it is a just, if you see this matrix, it's a reversely that NDVI is how much important with the LULC? Now it is 2 by 7. And here I will say land use, land cover is more important than the NDVI, that is 3.5. It is 1 by 3.5, nothing else. So it's a reverse. So if we make one side of this matrix, then other will be the main features. Similarly, you have land use, 10 type of land use. So you have to also, and in the every land use is not equally capable or equally importance for demarcating the groundwater potential zone. So they having the relative weightage. So that also we can find out, and we have also we have made that similar kind of matrix for each and individual features, sub features. Okay, and but using this scale, and this table actually summarize that. If you see, as I was trying to mention, as I was telling that land use, land covers, in this study I have classified 7. So if you can see the agriculture, crop, forestry, water body, study area, sandy area, wet land, agriculture, plantation, built up area, and agriculture fallow land. So if you see the groundwater prospect, this is subjective what I have used, and I have rank it, but this rank is not the same. If you just simply sum this and if you divided this, you will not get going to get this normalized weight. So it is basically, in background we have made that ASP matrix for each and individual. So say for example that built up area is less important compared to your forest land. So forest land having more prospect. So that way we have pairwise compare within the sub features, and then we have finally find out this uh, normalized weight using that ASP. Okay, so in this figure we can see that agriculture cropland is most influensive parameter we have given in the sub features category. So this will basically that equation I was mentioning and trying to explain to you. So basically what system will do in ArcGIS, and that equation also represented that this normalized weight will multiply this, then this. So just for example, so this will multiply, sorry, so this will multiply with this value, again this will value like this. So each and every time it will multiply individual sub features. So finally, and we will get finally that groundwater prospect zone. So similar way, that is 12 parameter we have used, and in the sub features parameter in the same methodology, as I explained, it made that individuals features and sub features importance and of the Jasmine matrix or ASP matrix or pairwise matrix. Then we have finalized this normalized weight, and this weight is not decided by us only. It also given the expertise view or expertise of this research. Then you can see just for in result discussion, I will not going to discuss elaborately what is the land use soil. So it's basically, as I mentioned, that land use source. You can make it if you know the remote sensing and GIS together. You can utilize the ADAS imaging, you can utilize the geomedia, or you can utilize also the 2D QGIS or ArcGIS. Then soil texture map, you can get it from ISRIC database, or you can get it from FAO database, or you can get it from our Indian database like National Bureau of Soil Science, Soil Survey and Land Use Planning database. Then surface geology, from that map already existing in your state government or central government agency. Then Richards rate, you can see. So further we have discretized the small size so that we can see the difference or very minute difference in the area for better to get the better influence of the Richards rate. Then drainage density, we have calculated the drainage rate in subbasin wise. Then rainfall map based on the your parameter, that is also interpolated in the ArcGIS using that uh, best fit equation, or you can say that is a semi-variogram using the semi-variogram. Then slope map, then this map you just can imagine it is a point data like that. So each and every pond, lake, river, big water, small water body, whatever existing within the watershed or within the study area, we have extracted from the Google Earth imagery. Because QuickBot you can purchase it. It's a submitter, you can get it. But during this study, that QuickBot or like this kind of study, uh, satellite imagery are not easily available and it's a costly affair. So we have extracted from the Google Earth engine, sorry, Google Earth Pro. Maybe you are all are using this. Then NDVI, then lineament density, and so that is a that very comprehensive way to represent or to visualize that it is basically method the uh, linear weighted average sum method. So simply we are just like that, we are placing an each and every layer on each other, and based on the numerical value or weightage assigned we get from the ASP, we may get this groundwater potential zone map. And this integration, this we can say it's the integration of the all thematic layer. So I am using these all are the thematic layer uh, because this is carrying only the specific information, not multi kind of information. Like this map is not showing rainfall as well as subsurface, so each and individual layer is representing individual features only. So for example, what is a map? Then we can say that is a topo sheet or who is provided by the Survey of India. In the same image or map, or in the same image you will get so many information, so many attribute. That's why it is called map, and these are all the same information. Slope, but slope classes will be there, but it's a various slope, only slope, no even geomorphology or soil database. So that's why it's called the thematic layer. And finally we will get this groundwater potential zone map. And so groundwater potential zone map with the well location. So you can see this dotted white spot, and there is number also. So we have also collected that pumping oil information from the government of Odisha, that Geological Survey and Investigation Department, and we have placed this groundwater, that oil existing or abandoned, to see the validity of the groundwater delineated groundwater potential zone map. Here we can see the each and every well, and that ID number it is here, and corresponding that ID is there, and their latitude and longitude, and their actual yield, that is actually design yield. Once they have drill that groundwater potential, drill that pumping well, and they measured that is actual yield, and then accordingly we have and this information we have extracted from the our potential zone map. So because this color, if you see, that red color is very good, though normally red used for dangerous or something bad, but here we have used the red for highlighting the which area having the most potential for groundwater exploration. Then deep green, then then light green, and then you'll so, and this subjective word we have extracted, and we have taken information from the map using that point information, then we have validated that disagree agree. So once this is coming under moderate or poor, so it is disagree. So this way, sorry, hello, hello, hello,
So hello.
yes, 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 please.
Sorry to interrupt you. How many slides actually we are left with?
No, you just give me time. I will slide might be more, but I will pack up within 10 minutes. It is okay for you?
Uh, Actually, next lecture is scheduled at 3:30. So
3:30. Okay. Okay. So 7 minutes I have, so I am just completing this. Yeah.
sorry for interruption.
Okay, no issue. That's fine. It's a management only. And so this is now accuracy. We can say it's 85% accuracy. So I am moving fast. Actually, I am going slow because I was thinking that it will go inside. Otherwise, it will go out. So I am not just moving fast. And so, as I mentioned, the sensitivity analysis and equation. So, in this slide, I can see that I will explain the conclusion. So, this slide is presenting basically the which parameter is how much sensitive, and if we omit one, what is the impact on the prospect zone. Okay, so this is one is conceptual diagram. Just it is, though it is not part of this today's lecture, but just for your information, or just for your knowledge, that how we can utilize this. So once I got this potential zone map, so this is only the quantitative aspect, but we don't know the qualitative aspect. So I have used this map for the quality check. So once I will get the quality as well as the quantity aspect both together, then I may able to explore further. Yes, what should be the exact drilling point for me for the further new exploration of the groundwater zone. So this is quality. This is a classification. Based on this classification and based on the spatial database available with me, and I have categorized. Say for example, SAR value. So less than 10, we know that excellent. But in our case also, the data says the groundwater quality under this category. So and here in this map, you will find this is only the same color I have put it. This map is not showing that. That the variation of the EC or variation of the TDS or variation of the sodium percentage, it is showing basically this based on this classification in which class our data is there. So basically this map is a derived from the spatial variation map of the EC. Based on this category of classes, we have reclassified that the special variation map, and we have finalized that, and that some we will see in this map some area is coming like that. So this is class 1, this is class 2, like this is permeability index. So if we see this is good, so few observation oil or pumping oil is coming on this category, like that. Finally, get we can get this map or in tabular form that that same observation oil or same groundwater pumping oil, what what is going on. So A means accepted, A here this A agree, disagree, partially agree, like that. So that way we have seen, and that how much how it is actually this my groundwater potential zone is qualitative, it is certifying or not. So both way we can see it's a satisfying that quality as well as the quantity. So so one can say that yes, your groundwater potential, and you can go anywhere with the prospect map for drilling or for extraction of the groundwater further without bothering, because the quality as well as the quantity is both checked. Though it is not the first and it is actually maybe that, as I mentioned, that 85% accuracy level is there. So sometimes you may fail, but chances of failure is less. So what is the summary? Now, groundwater potential zone map was classified into four category. That major group under coming under good category, that is 43.57, and then very good, that is 36.39. Basically this area actually coastal belt, and that is a deposited. So that prospect is very high for this area basically. Then validation accuracy is 85%, as I mentioned. Sensitive analysis inferred that the NDBI, surface geology, and soil thematic layer are the most sensitive parameters. So groundwater potential zone map can be used as a tool for identification of possible location for construction of new tube wells, may reduce the economic loss from failure. Integration of remote sensing GIS and ASP together act as a handy tool for effective water management. So beside, just for your information as you are a student, so besides with that, I already mentioned that ASP, then gray ASP, then weight of evidence, then frequency ratio method, index of entropy, and logistic regression, and evidence of belief function. You can utilize this. So this is one example of the frequency ratio method. So you can see number of spring, and if you divide by the total number of spring, then you will get the percentage of the spring, and then if you, and at the same time that number of pixels, so percentage of pixels. So with this ratio you will get that FR value, that is a frequency ratio method. So for example, I am just showing you, so you can explore it further. And then acknowledgement, I wish to convey my heartful thanks to BIT Shindre Dhanbad head Department of Civil Engineering and coordinator Dr. Kamal Kumari for inviting me as the guest speaker on this 5 days workshop, and I wish to express my deep sense of gratitude and sincere admiration to my director Dr. Emodu and head of the division Dr. R.K. Singh. And thank you all for your patience for listening me and giving this opportunity. That's all from my side. So I hope I have
Thank you.
completed 2 minutes before this.
Enriched our understanding of this domain. Now we request Dr. Iqbal Sheikh Sir, Assistant Professor, Civil Engineering Department, BIT Sindri, to.
May leave? I may leave?
Yes, sir. Yes, sir.
Okay, okay. Thank you. Or any further future if you want to know more, because it's a very short time, short period I have just cover up. Okay, thank you all. Okay, all the best.
Thank you, sir.